This is an interesting graph that I found online that actually contains many piecewise functions. So what we're looking at here is we're looking at various different models of Teslas. We've got 3 different models here, and what we're seeing is the power output. So if we're dealing with the MS60, if that car is going between 0 and about 42 miles an hour, it puts out about just a little less than 450, let's call it about 430 Newton meters of power. And then after you get above the 42 miles an hour, you can see that the power starts to decrease. Now, this is not, as you can see, a straight line. But what we're going to do is we're going to model it with a straight line. It's pretty straight for a while, a little bit of curve at the end. So we're going to model it by a straight line. We're going to do our best. On the other hand, if you're dealing with the Model S60, this is the kilowatts that the battery is being drained from. So you can see if you're going less than 40 miles an hour, 42 miles an hour, your kilowatt usage is going up. Then it's kind of interesting. You get to 42 miles an hour, your kilowatts stay constant for a while up to you get to about 67 or so, and then the amount of kilowatts you expend begin to decrease again. And I think that kind of makes sense that they begin to decrease because what's happening is your power output is going down. Since your power output is going down, the kilowatts you're using go down. And you can see we have that kind of pattern for all 3 different models of the Tesla. Lots of power at the beginning. Power starts to wane off. Kilowatt usage goes up significantly at first, levels off, then goes down. Okay, so what we're going to do is we're going to write 2 different piecewise functions here. As you can see, there are really 6. There's the solid red, the solid green, the solid blue, and then there's the dotted red, the dotted green, the dotted blue. We're going to write 2 piecewise functions, and we're always going to use the blue one. So write a piecewise defined function for the power of the M260. So power is the blue line. All right. So what I can see is I'm going to have 2 pieces. I'll use P for power, and I'm going to have 2 pieces. And I like to write the if parts first when I'm looking at a graph. So the first piece goes all the way up to about 42 miles an hour. So I'm going to use S for speed. So this one happens as long as speed is less than or equal to 42. And then the second piece is going to be this part, and that happens as long as speed is greater than 42. So when I get all done, my answer is going to look like that. Now comes the easy part, and then the hard part. This part's the easy part. This is constant. So this is simply, it looks like it's about 430. So notice I'm approximating there. I don't know that it's exactly 430, but I'm going to call it 430. And then comes the hard part. What we have to do is we have to pick 2 points and make a line. So I'm going to try to make a line that kind of comes close to all of these. It's going to start here, and it's going to be above a little bit, and it's going to be down a little bit. So I'm going to maybe end it right about here. So I'm going to, I wish I had a ruler. Maybe I can use my calculator here. So I'm going to approximate that curve by a line. That line right there. So the line's above sometimes, it's below sometimes, but it kind of comes close. In the future in this course, we will talk about how to deal with curves, and maybe we could come back to this problem and try to find a curve that fits. That would be interesting. Anyway, to find this equation, I now have 2 points. I have this point right here, which is 42,430. And then I have this point right here, which is, I'm going to call it, I missed that point when I do my line, I'm going to call it 105, 100. And then we go back to what we learned a few sections ago. If I have 2 points, I find the slope. So my slope is going to be 430 minus 100 divided by 42 minus 105. I type that into my calculator. 430 minus 100 divided by more than one thing on bottom, so put it in parentheses. 42 minus 105. Minus 5.2, we'll call it. And then I can look at these 2 points and I can see, unfortunately, I do not know the y-intercept. I don't have a 0 in either of those spots. So I'm going to go P minus 430 equals minus 5.2 times S minus 42. I use the y minus y1 equals m times x minus x1 formula, except I'm using P and S instead of X and Y. So here's what I would write over here. I want the P thing, so I would simply add the 430. So the formula over here is minus 5.2 times S minus 42 plus 430. And if you want it to be fancy, you could go ahead and distribute this minus 5.2 through and then combine like terms. I don't care to be that fancy. I'm fine with it written just like that. Okay, now we're going to repeat finding a piecewise function, except we're now going to do the kilowatts. And the kilowatts is the dotted blue line. Not dotted blue line, that's very poor wording. It's the dotted blue function, because we can see it's got part of a line, then it's got constant, and then it's got another part of a line. So, this is our first example of a piecewise function that has 3 pieces. So we're going to write kilowatt equals, and we're going to have 3 pieces. The first piece happens as long as our speed is less than 42. The second piece is this constant piece that starts at 42 and ends at about 68. Oops, I want 42 less than S, less than 68. And then the third piece starts at 68 and goes forever. Alright, so again, I like to write my big parenthesis and then I like to write my if parts first. Now I got to find 3 equations. So the first one starts here at 0, 0, and it ends at 42, 200. Alright, I'm going to need some more space to write, so I'm going to go to the back. Let's see if I got a different piece of paper. Here we go. So this one we said starts at 0, 0. Show you the graph again. And it ends at 42, 225. Alright, I find my slope. Slope is 225 minus 0 over 42 minus 0. 25 over 42, 5.4. And then this is very handy. This tells us our b is 0. So for this one, I would go ahead and use y equals mx plus b, because I know the b number, because I have a 0 right there. So I'm going to have kilowatts is 5.4 s plus 0. Alright, so there's my first equation. 5.4 s. Second one's the easy one, because the second one is just constant, not changing it at all. So that's just 225. In the middle here, it's always 225. The last one, again, I gotta pick a couple points. So I'm gonna have, I called it 68, 225. And then I'll pick a point down here, I guess, Right here looks like a good one. 68, 225, just so you can see that one. And then this one is 120, 125. So my slope is 125 minus 225 divided by 120 minus 68. That's minus 100 over 120 minus 68. Calculator tells me that's 52. Negative 100 divided by 52 is negative 1.9. Alright, so much like last time, I'm going to use y minus y1 is m times x minus x1. But I don't have y, I have kilowatts minus one of the y numbers. I'm going to use the second point this time. I'm going to use I'm going to use the first one again. 225 equals m, negative 1.9, times, I'm not using x, I'm using speed, minus 68. Okay, so again, to write that here, I would move the 225 over to the other side, and I'm going to be lazy, I'm not going to simplify. So it would be minus 1.9 times s minus 68 plus 225. Okay, so you can see writing these piecewise equations is kind of a challenge. And it's a challenge because we really have to understand what we did back a few sections ago about writing equations of lines, and quite often we have to write more than one of them. This one was easy because it was just horizontal, but writing these two go back to like the first two sections we did earlier this semester. So you might have to go back and review writing equations of lines. Same deal here. This one was easy because it was just constant. But again, this goes back to what we did a while ago. So, challenging section, a lot of new stuff for you, and then it's got a combination of a lot of old stuff too. Alright, here's the exciting news. This section isn't done. There's going to be more to it. There's going to be more videos. We're going to get away from word problem kind of things and just go kind of to traditional algebra problems. But I wanted you to see where piecewise functions come from. There's actually a lot of them in life. This is real, actually. This is right from the Tesla website. And then the problem on Social Security tax that we did, that one was real too. I pulled that one right from a federal government website. The dog grooming one, sort of real. I made up the numbers. But I did look online, and usually to get your dog groomed, there was some sort of thing like that where you paid a flat rate for a while when your dog was small, and then you paid more when your dog got big. But it was more confusing than that because it also depended on if your dog had long hair or short hair, or if your dog was heavily matted or not. So there was more variables involved there, but I didn't want to get into that much complication. Other places where you might see piecewise defined functions. If you look carefully at your electric bill or your gas bill, those are piecewise. They charge you a small amount, actually they charge you a lot at first for your electricity, and then the more you use, they have drop-offs. And the same thing works with natural gas. Another place you might see a piecewise function is with your cell phone plan. A lot of cell phone plans, you pay for so much data per month, and if you go over that data, you have to pay more money. So you pay a flat rate for so much data, and when you exceed that data, you pay more money. So there are actually lots of good examples out there in the world of piecewise functions.